Few concepts in the history of human thought are as enigmatic and overwhelming as the origin of the universe. Even before there was time, space, matter, or any elementary particle, there was nothing. An absolute nothingness, without direction, form, or vibration. No stars, no planets, no gravitational force to pull, no light to travel, no mind to perceive. This primordial void, incomprehensible to the human mind, is the backdrop for one of the grandest and most defining events in existence, the Big Bang. Modern science, supported by observational evidence and mathematical predictions, holds that approximately 13.8 billion years ago, all the energy and matter in the universe was concentrated in an infinitely small, dense, and hot point, a singularity that broke its inertia, not with an explosion, but with a dizzying expansion, creating space-time itself, the fabric upon which everything unfolds. This initial expansion did not resemble an explosion in empty space, but rather the very creation of space. Space wasn't filled, it came into being. Time didn't start ticking after a pause, it began to exist. That instant, zero marks the simultaneous birth of all the physical laws that would shape the cosmos: gravity, electromagnetism, and the strong and weak nuclear forces. From this almost mystical origin, the universe underwent a phase of cosmic inflation. In less than a billionth of a trillionth of a second, space expanded exponentially. This phase is responsible for the homogeneity of the observable universe today, where distant galaxies share physical properties despite being separated by billions of light years. Soon after inflation, the released energy began to cool, giving rise to the first subatomic particles. Quarks, leptons, and gluons began to interact under extreme conditions. In this primordial soup, the particles that would one day form atoms were still unstable, dissolving in energetic collisions and reorganizing within mere instants. It was through the universe's gradual cooling that quarks began to combine into protons and neutrons, the particles that would later form the nuclei of the first atoms. During the universe's first 3 minutes of existence, a process known as primordial nucleosynthesis occurred. In this brief window, protons and neutrons combined to form the first nuclei of hydrogen and helium, the simplest and most abundant elements in the cosmos to this day. However, atoms as we know them still couldn't exist. The density and temperature were too high for electrons to stabilize around these nuclei, resulting in a universe dominated by a plasma of charged particles that absorbed and scattered light, an opaque era where no electromagnetic radiation could travel freely. Only 380,000 years after the Big Bang did the universe's expansion and cooling allow the first true atoms to form. Electrons and nuclei united into neutral atoms, and light, finally liberated, began to travel in straight lines across the cosmos. This moment is recorded in the famous cosmic microwave background radiation, a thermal signature that still fills the universe and can be observed today with radio telescopes. This radiation is one of the pillars of modern cosmology, a photograph of the baby universe, revealing density fluctuations that, billions of years later, would give rise to stars, galaxies, and planets. This story, which begins in the most absolute absence of everything, is told not only by physics, but by the light that still travels. Every photon, every wave, every vibrating field in the vacuum is a clue revealing the deep past of reality. The universe was not born to be seen, but it became visible. It was not born to be heard, but it began to emit music. And we, at the end of this evolutionary line, are now the eyes and ears that witness, narrate, and study this cosmic story. A story we are only beginning to understand. The history of the universe began with a moment so brief, so minuscule, that it defies all intuition. The first fraction of a second after the Big Bang cannot be understood using the concepts of everyday life. We are talking about a time shorter than 1/10 of a trillionth of a second. It was during this unimaginably small interval that the universe experienced a phenomenon known as cosmic inflation, a rapid, exponential, and extremely violent expansion that multiplied the size of the universe by magnitudes beyond comprehension. This expansion did not happen within space. It was chaos of space itself, stretching like an invisible fabric in all directions, simultaneously creating time, matter, energy, and physical laws. During this initial moment, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were still unified in a single superforce. The universe was a field of pure energy, extremely hot and dense, where there were no stable particles, no shapes, no separation, but as space expanded, the temperature began to fall, and like a carefully orchestrated cooling, this energy began to fracture into distinct components, giving rise to the forces we now know. First, gravity decoupled, and then the nuclear and electromagnetic forces split. These cosmic phase transitions were like cracks forming in a freezing lake, points where perfect symmetry broke, giving rise to new physical behaviors. Shortly after, the universe became a furious soup of elementary particles. Quarks and antiquarks appeared by the trillions, colliding and annihilating each other in flashes of pure energy. For every billion pairs destroyed, a single particle of matter survived. This tiny asymmetry between matter and antimatter, whose origin remains one of modern physics' greatest mysteries, allowed the material universe to exist. If the quantities had been exactly equal, everything would have annihilated, and there would be no stars, planets, or life. The balance of the cosmos as we know it depended on a small imbalance in the fundamental laws of creation. Between 10 to the negative 30 seconds and 1 microsecond after the Big Bang, quarks began to combine, giving rise to the first protons and neutrons. Gluons, the mediator particles of the strong nuclear force, held these quarks together in triplets that would become the core of each atom. Meanwhile, other particles like electrons and neutrinos also emerged and interacted. The density was so intense that, even with less than 1 second of existence, the universe already held more energy per cubic centimeter than the interior of a modern star. Time had begun to flow, but still had no meaning as we understand it, because nothing yet existed to measure it. A single second in that era was an ocean of transformation, and so even in this primordial phase, the fundamental building blocks of all matter began to take shape. As cooling continued, the universe moved from a chaotic, hyperdense, radiant state to a more structured one, where particles now had mass and defined properties. This process lasted only the first 3 minutes of the universe, but it defined all future possibilities. The laws of physics, the elemental proportions, the conditions for gravity to act effectively, and the very pace at which the cosmos would evolve. Every instant of these first seconds was like a primal beat of a cosmic drum, and its reverberation still echoes today in the structures of space. It was in this stage that the background radiation was seeded, even though it would only become visible hundreds of thousands of years later. The quantum fluctuations that occurred during inflation were stretched and magnified, leaving regions with slightly different densities. These small variations would become, billions of years later, galaxies and superclusters. In other words, the origin of galaxies was already written in the microscopic irregularities of the primordial vacuum. Thus, the largest objects in the universe, galaxies with hundreds of billions of stars, were born from the tiniest fluctuations of quantum energy, the macro and the micro dancing in unison in the first moments of time. With less than 1 second of existence, the universe had already set its rate of expansion, configured its fundamental forces, and initiated the process of matter formation. It was a violent, energetic, brilliant, and promising child. Everything we see today, stars, mountains, oceans, and the eyes that behold them, was born from these original moments. Time began to make sense. Space became a stage, and matter began, slowly, to organize itself. After the first seconds of creative chaos, the universe entered a decisive phase, continuous cooling and the birth of structure. Time now flowed toward complexity, and although it was still a hostile place, conditions were gradually becoming more gentle. Between the third minute and the next 380,000 years, the universe was an ocean of radiation and free particles, a dense, hot plasma where light could not travel. Electrons, still extremely energetic, were prevented from joining the nuclei formed during the first minutes. Every attempt at atomic formation was disrupted by the intense energy of the photons that filled the cosmos, as if the universe were a glowing fog where nothing was visible and everything remained in constant flux. During this long period, known as the plasma era, the universe was opaque. Light was constantly absorbed and re-emitted by collisions between electrons and photons. There was no transparency, no direction, All visible energy was trapped in this sea of electrically charged particles, but time, patient and absolute, did its part. Constant expansion diluted the density of the universe, and with that, its temperature dropped gradually. From billions to millions, then to hundreds of thousands of degrees Kelvin, the universe began to cool enough to allow a silent revolution, recombination. Recombination was the process in which free electrons were finally able to bind with hydrogen and helium nuclei, forming neutral atoms. This occurred around 380,000 years after the Big Bang, when the temperature fell to approximately 3,000 degrees Kelvin. With electrons now anchored around nuclei, radiation stopped scattering, and light, for the first time, could travel freely through the cosmos. This transition marked the end of the universe's opacity and the birth of the cosmic microwave background, a kind of thermal echo of space-time's birth, which still fills the universe in all directions today. This radiation is not a burst of visible light, but a faint, almost uniform electromagnetic wave that permeates the cosmos like a thermal backdrop. Today it appears in the form of microwaves, and its detection in 1965 by scientists Arno Penzias and Robert Wilson was one of the most important milestones in modern cosmology. They didn't know what they were picking up, a constant noise in their antennas, until theorists explained they were listening to the baby universe, emitting its first light. That discovery is thus considered the first photograph of the universe, and its tiny temperature variations are maps of the seeds of future galaxies. With light now free to travel, the universe became transparent. For the first time, it lit up to our eyes, though no eyes yet existed to see it. But photons began a journey that continues to this day, crossing space and carrying precious information about the cosmos's childhood. Meanwhile, matter, now organized into neutral atoms, began to feel the effects of gravity more efficiently. Small density fluctuations, which emerged from the quantum fluctuations amplified by inflation, started to clump together. Slightly denser regions attracted more matter, generating a cycle of gravitational collapse that would lead to the formation of the first cosmic structures. For hundreds of millions of years after recombination, the universe plunged into a new kind of darkness. This phase is known as the Cosmic Dark Ages. Although light was now free, there were still no sources of visible emission, no stars, no planets, no galaxies, only hydrogen, helium, and the gravitational dance that slowly gathered the first clouds of gas. The universe was a quiet and cold place, expanding more and more, preparing itself for the next great event, the birth of the first stars. This phase of cosmic gestation is crucial. It was in this void, in this darkness, that matter began to organize into massive gravitational filaments, the cosmic web that today connects galaxies, clusters, and superstructures. Gravity sculpted the universe into great voids and dense regions, like an invisible tapestry shaping the future. The primordial plasma, now converted into neutral gas, accumulated in the densest regions, being compressed until internal pressure and temperature were high enough to ignite nuclear fire. The cooling of the universe was not merely a loss of heat. It was an ordered process that allowed complexity to arise. It created the conditions for the formation of the first structures, gave rise to cosmic transparency, and released the radiation we now use to reconstruct the universe's history. It was a silent moment, but an absolutely transformative one. The universe had created matter. Now it was creating the conditions for brilliance. After the great silence of recombination, the universe plunged into the deepest darkness of its existence. It was the time of the Cosmic Dark Ages, an interval that lasted hundreds of millions of years when light was already free to travel, but no active light sources yet existed. Stars had not yet been born, and galaxies were merely gravitational promises sculpted in the invisible. This dark, silent, and cold phase was not an absolute void, but rather a universe in gestation, where matter slowly organized under the action of gravity. Tiny density perturbations, seeds left behind by quantum fluctuations during inflation, began attracting more matter around them, forming vast clouds of hydrogen and helium that, in silent collapses, would give rise to the first points of light. These first stars, known as population 3 stars, were the first objects to transform the universe from a cold, homogeneous environment into a living and structured space. Formed almost exclusively from primordial hydrogen and helium, since heavier elements did not yet exist, these stars were unstable giants, often hundreds of times more massive than the Sun. With no metals or interstellar dust to scatter radiation and slow contraction, they collapsed quickly, reaching extreme nuclear temperatures in their cores and igniting fusion reactions never before seen in the universe. Their glow was intense, bluish, and brief. They lived only a few million years, but during their short existence, they forever changed the cosmos. The birth of these stars marks the end of the Dark Ages and the beginning of the epoch of ionization. The intense ultraviolet radiation emitted by these giants ionized the surrounding neutral hydrogen, creating expanding bubbles of ionized gas that merged over time. With each new star formed and extinguished, the universe became more ionized and transparent, as if giant beacons were lighting up in the cosmic dark, gradually lifting the curtain hiding the universe's new structure. This slow process was essential for allowing light to travel long distances without being absorbed, making it possible for modern telescopes to observe the most ancient galaxies. As more stars formed, they began grouping into proto-galaxies, dense structures composed of gas, dust, and dark matter. Gravity, like an invisible sculptor, shaped these concentrations into increasingly complex formations. The earliest galaxies did not resemble the majestic spirals we see today. They were irregular, turbulent, with extremely high rates of star formation and supernovae exploding constantly. The violence of the birth of the first stars created shocks and interstellar winds that redistributed matter, creating continuous cycles of destruction and renewal. Within these proto-galaxies, new generations of stars began to emerge. Unlike the population 3 giants, these stars contained traces of the heavier elements produced by their predecessors: carbon, oxygen, iron, enriching the interstellar medium and enabling the formation of planets and more complex molecules. Each supernova that exploded seeded the universe with new ingredients, and through this stellar life and death cycle, the cosmos became increasingly rich, diverse, and complex. In parallel, primordial black holes began to form. Many emerged from the collapse of the first massive stars. These extreme objects, with gravitational fields strong enough to trap light, became the cause of many young galaxies. Over time, they grew by absorbing surrounding matter and merging with other black holes, forming the supermassive black holes that now reside at the center of most galaxies, including our own Milky Way. During this transitional era, the universe slowly lit up. Dense active regions emitting light and heat spread across a backdrop still dark and cold. It was like witnessing the first cosmic dawn, timid lights emerging in an ocean of shadows, and it was this contrast between darkness and radiation that defined the great flows of visible matter, guiding its movement over the billions of years that followed. The formation of the first stars represented more than the beginning of luminosity in the universe. It marked the birth of cosmic alchemy. It was within these stars that the heavy elements, essential for the formation of planets, oceans, and life, were forged. The iron in our blood, the oxygen we breathe, the calcium in our bones, all were cooked in stellar furnaces that exploded billions of years before our sun was born. This atomic legacy links every living being to the explosion of a distant star and makes our existence an inevitable continuation of cosmic history. With the birth of the first stars and the ignition of the earliest galaxies, the universe entered a new fundamental transformation, the epoch of ionization. This cosmic period, spanning from approximately 400 million to 1 billion years after the Big Bang, marks the moment when the extreme radiation produced by the first generations of stars and galaxies began to ionize the neutral hydrogen that had dominated the cosmos since recombination. This slow and progressive process had a direct impact on the structure and transparency of the universe, determining how light would travel across cosmic distances to eventually reach our telescopes billions of years later. It was as if the universe were being lit from within, not suddenly but by millions of small candles expanding in every direction, slowly brightening the deep space. During the Dark Ages, the universe was filled with neutral hydrogen atoms that easily absorbed high-energy photons, rendering the cosmos opaque to background light. But as the first massive stars, quasars, and galaxies began emitting large amounts of ultraviolet radiation, these atoms were once again broken into protons and electrons, the process of ionization. This breakdown returned atoms to their ionized state, the same that existed in the early universe, but now driven not by primordial heat, but by the power of the first luminous sources of cosmic structure. In this sense, the universe became a plasma again, but a rarefied, transparent plasma shaped by light. Reionization did not happen uniformly. Bubbles of ionized gas formed around the first stars and galaxies, slowly expanding throughout the universe. As more luminous objects emerged, these bubbles merged and grew, enlarging the regions of transparent space. This process took hundreds of millions of years, and by its end, the universe had become almost entirely reionized, a condition that persists to this day. This transition allowed light from distant sources to travel for billions of light years without being absorbed, making it possible to study the deep cosmos through the light emitted during the earliest phases of universal history. While radiation shaped the intergalactic medium, another silent protagonist played its part: dark matter. Invisible yet dominant in mass, dark matter played a vital role in the formation of galaxies and cosmic structures. Its gravitational interactions created wells of attraction where gas accumulated, forming stars and galactic clusters. Without it, the visible universe would not have been able to organize itself so quickly. Dark matter acted as an invisible web, a cosmic net where baryonic matter, the ordinary matter, condensed. The light from stars revealed this web, but its structure was determined by something that neither emitted nor absorbed light. Another crucial element in this process was the formation of the first quasars, active galactic nuclei powered by newly born supermassive black holes. These exotic structures emitted colossal amounts of radiation, often outshining all the stars in their host galaxies combined. As a result, quasars became powerful sources of reionization, accelerating the process in their cosmic neighborhoods. Their surprisingly early existence continues to challenge current models of black hole and galaxy formation, raising questions about the efficiency of mass accretion and the merging of structures in the early universe. As the epoch of reionization came to an end, the universe showed the first signs of structural maturity. Young galaxies became more organized. Star formation was still intense but began to stabilize. Ionized regions now dominated intergalactic space, allowing light to travel freely and making the cosmos transparent, as it is today. This cosmic scenery, a web of dark matter illuminated by vibrant galaxies, threaded with heated gas filaments and crowned with shimmering quasars, became the foundation upon which future generations of stars, planets, and life forms would be built. The epoch of reionization was, therefore, more than a period of physical transformation. It was the ignition of the universe as an active system, where energy and structure began to intertwine on massive scales. The cosmos was no longer a neutral and obscure sea. It became a dynamic, interactive, visually complex and luminous realm. Without this phase, modern galaxies, planets, and even the possibility of life as we know it would have been impossible. It was the moment when the fire of creation spread through the veins of the universe, and primordial darkness was finally conquered by light. With the end of the epoch of reionization, the universe had moved from primordial darkness to visible complexity. In this new landscape, galaxies co-emerged as the first large-scale organized cosmic structures, true nurseries of stars, dark matter, gas, and chemical elements. These colossal systems, which today captivate us with their variety of forms and scales, began as turbulent concentrations of hydrogen gas and dark matter, held together by gravity in slow-spinning cosmic whirlpools that organized matter into increasingly dense regions. The formation of galaxies was a natural outcome of the primordial fluctuations left in the universe after inflation and amplified over billions of years of expansion. These structures were born from the gravitational collapse of cold gas clouds, accumulated within halos of dark matter. As these clouds lost thermal and angular energy, they became unstable, triggering star formation within them. This gave rise to the first galactic cores, stellar groupings fueled by fresh gas and surrounded by gravitational fields dominated by dark matter. These cores merged with others nearby, initiating a chaotic and continuous process of mergers and interactions that shaped galaxies into various sizes and forms. The cosmos became a stage for titanic collisions between protostructures, where each impact redistributed gas, stars, and gravitational energy. Over time, three main types of galaxies began to stand out: spiral, elliptical, and irregular. Spiral galaxies, like our Milky Way, acquired their characteristic shape through the orderly rotation of their gas and star disks, molded by centrifugal forces and internal gravitational interactions. Elliptical galaxies, often the result of violent mergers between smaller galaxies, displayed a more spherical distribution of stars, with little ongoing star formation. Finally, irregular galaxies reflected the chaotic nature of their formation, lacking defined symmetry and common in the primordial universe, where structures were still in transition. Our Milky Way, in particular, has a history marked by multiple galactic mergers. It is believed to have absorbed dozens of dwarf galaxies over billions of years, incorporating their stars, gases, and dark matter. At its center lies a supermassive black hole, with millions of times the mass of the Sun, around which all of the galaxy's stars orbit. The galaxy consists of a flat disk containing spiral arms rich in star formation, a dense central bulge, and a diffuse halo of stars and dark matter. Each of these parts reflects different phases of galactic formation, from cold gas accretion to the collapse of stellar clusters. Beyond stars, galaxies contain clouds of unmolecular hydrogen, interstellar dust, cosmic rays, magnetic fields, and complex orbital structures such as globular clusters and planetary systems. They function as cosmic ecosystems, with active regions where new stars are born and dead zones where gas has been depleted or expelled by stellar explosions. The interaction between stars, gas, and radiation generates constant cycles of birth and death, driving the structural growth and chemical evolution of galaxies. Young galaxies are chemically poor in metals, but as stellar cycles continue, elements like carbon, oxygen, iron, and silicon accumulate, enabling the formation of rocky planets and complex compounds. Another impressive aspect of galaxies is their gravitational connectivity. They are not isolated, but organized into clusters and superclusters, linked by filaments of dark matter and hot gas. This hierarchical organization forms what we call the cosmic web, a colossal network that spans the entire observable universe, revealing a spongy, large-scale structure where cosmic voids and filaments shape the fabric of the cosmos. This web is not only visually stunning, it is also a map of the universe's gravitational history, where every point of light represents a chapter in cosmic evolution. The formation of galaxies was also crucial for the emergence of morphological diversity and the distribution of visible energy across the universe. Without them, there would be no planets, no complex chemistry, and no long-lived stars like the Sun. Each galaxy holds its own chronology, a unique signature of interaction between baryonic matter and dark matter, between gravity and radiation, between chaos and order. Studying them is studying the very history of the universe in microscale. Each star like a letter, each nebula like a word, each black hole like a period. Galaxies are, therefore, the pillars of cosmic complexity. In them, matter reorganized from primordial gas into extraordinary forms of beauty, balance, and energy. They sustain the continuous glow of the universe, spreading light, heat, and chemical elements for billions of years, and it was within them that, much later, planets like Earth would arise, tiny fragments orbiting common stars in habitable regions of gigantic galaxies. The history of the universe, told through billions of stars, pulses in every galaxy like a living memory of creation. Amid the vastness of the Milky Way, a galaxy with hundreds of billions of stars, a seemingly ordinary cloud of gas and dust began behaving in a singular way about 4,600,000,000 years ago. This cloud, located in one of the galaxy's spiral arms and known as the primordial solar nebula, would give rise to what we now call the solar system. Composed mostly of hydrogen and helium, but also enriched with heavier elements, forged by previous generations of stars and spread by supernovae, this cloud was a direct legacy of the stellar cycle that had transformed the universe into a chemically rich and complex tapestry. And it was this atomic inheritance that set the stage for the emergence of the Sun, the planets, and eventually life. The formation of the solar system began with the gravitational collapse of this nebula, likely triggered by a shock wave from a nearby supernova explosion. Gravity pulled the material toward the center of the cloud, creating a protostar, the embryo of the Sun. As more matter accumulated, the pressure and temperature in the protostar's core increased until it reached the critical point for the ignition of nuclear fusion. This was the moment the Sun was born, not with an explosive flash, but with a steady glow fueled by the conversion of hydrogen into helium, releasing energy in a balanced and sustained manner. Around it, a disk of gas and dust spun rapidly, flattening out and initiating the formation of planetary bodies. This protoplanetary disk was a dynamic mixture of chemical elements: hydrogen, helium, carbon, oxygen, silicon, iron, arranged in regions of varying temperature. In the areas closest to the Sun, only the most refractory materials, such as metals and silicates, could condense, which favored the formation of rocky planets: Mercury, Venus, Earth, and Mars. In the more distant regions, where solar heat was less intense, volatile compounds such as water, methane, and ammonia could freeze, allowing the formation of gas and ice giants like Jupiter, Saturn, Uranus, and Neptune. This differentiation process created two major domains in the solar system: the inner system, dense and rocky, and the outer system, massive and dominated by thick atmospheres and numerous moons. Planet formation occurred through accretion of matter, where tiny dust particles collided and fused, forming clumps that grew into planetesimals, bodies tens to hundreds of kilometers wide. These, in turn, collided violently, merging into protoplanets. In an environment of frequent and chaotic collisions, only the most stable and massive bodies survived, clearing their orbits and establishing the planetary configurations we observe today. Earth, during this phase, was violently struck by a Mars-sized body, known by scientists as Theia, whose ejected material into space coalesced to form the Moon cell. This event, although catastrophic, was essential in stabilizing the planet's axial tilt and establishing tides fundamental to future life dynamics. While planets were forming, millions of smaller objects, asteroids, comets, moons, and dwarf planets, also emerged from the protoplanetary disk. Many were ejected to outer regions, forming the Kuiper Belt and the Oort cloud, true reservoirs of ice and rock, fossil remnants of the original formation. Others collided with forming planets, including Earth, delivering volatile compounds, water, and organic molecules. It is believed that much of Earth's ocean water came from primitive comets, which acted as cosmic messengers, bringing key ingredients for the chemistry of life. The Sun, the gravitational center of the entire system, reached stability as a Uji-type spectral star, with an estimated lifespan of about 10 billion years. It emits energy steadily, creating the thermal and luminous conditions for at least one of its planets to develop liquid oceans, atmosphere, climate, and biochemical cycles, rare and precious conditions in the cosmos. Earth, positioned in the so-called habitable zone, became a singular oasis of chemical complexity thanks to the ideal combination of mass, solar distance, protective magnetic field, and internal geological activity. The formation of the solar system was not an isolated event, but part of a greater cycle that connects the birth and death of stars to the emergence of planets and eventually life. Every iron atom in our blood, every carbon molecule in our bodies, every calcium crystal in our bones, all of it was forged in previous generations of stars that died in cosmic cataclysms and left their remains as seeds for future worlds. When we look up at the night sky and see the planets and their moons, we are seeing living chapters of the universe's history, gathered around a common star, one that, for us, represents the heart of our personal cosmos. Amid the creative chaos of the primordial solar system, Earth emerged as a point of balance between extremes. Neither too hot like Venus, nor too cold like Mars, the third planet from the Sun gathered the ideal conditions to become something extraordinary, a living world. With a solid surface, protective atmosphere, active magnetic field, and, above all, stunner liquid water, Earth established itself as a natural laboratory where cosmic elements began interacting in increasingly complex ways. The planet's formation was violent, Constant bombardment by asteroids and comets, intense volcanic activity, and the collision with Theia, which formed the Moon, shaped its landscape, composition, and axial tilt. Yet it was precisely in this turbulent environment that the ingredients of life began to mix. During its first 100 million years, Earth was a scorching inferno. Its crust was still forming. Magma bubbled on the surface, and the atmosphere was thick and toxic, composed of carbon dioxide, methane, water vapor, and ammonia. There was no free oxygen, no tranquil oceans, only electric storms, extreme heat, and frequent cosmic impacts. And yet, sometime between 8 and 4 billion years ago, something extraordinary occurred. Life emerged. The origin of life remains one of science's greatest mysteries. There are many hypotheses, but no certainty. One widely accepted theory suggests that complex organic molecules formed spontaneously in energy-rich environments, such as underwater hydrothermal vents or shallow pools exposed to sunlight and lightning, from simple compounds like methane, ammonia, and water. These molecules began to interact, form chains, and eventually develop the ability to replicate. A molecule similar to DNA is considered one of the earliest forms of genetic material. Capable of storing information and catalyzing reactions, it may have been the precursor to modern biochemistry. Life therefore began microscopically as simple unicellular organisms called prokaryotes, multiplying in aquatic environments. For billions of years, Earth was dominated by these life forms invisible to the naked eye, but absolutely essential. They transformed the atmosphere's composition, releasing oxygen through cyanobacterial photosynthesis, a revolutionary process that forever changed the planet. This event, known as the Great Oxidation, occurred about 2.4 billion years ago and made oxygen a permanent component of Earth's atmosphere. Although it caused mass extinctions among anaerobic organisms, it also paved the way for new metabolic forms and eventually multicellular life. Simultaneously, the presence of oxygen enabled the formation of the ozone layer, protecting the surface from ultraviolet radiation and allowing life to begin colonizing shallower sunlit environments, and later, even dry land. During this period, Earth underwent dramatic transformations. Continental drift, supercontinents like Rodinia and later Harpangaea, extreme climate shifts like global ice ages, known as snowball Earth's events, and mass extinctions all shaped the planet's ecological landscape. Yet, life persisted, it evolved, it adapted. Eukaryotic cells, with organized nuclei and complex internal structures, emerged through symbiosis, when one cell engulfed another and began to cooperate with it. This evolutionary leap was essential for the formation of multicellular organisms, which specialized in different functions, forming tissues, organs, and eventually organisms with nervous systems, eyes, fins, and limbs. Around 500 million years ago, during the Cambrian explosion, an extraordinary diversity of life forms appeared in the oceans. Marine invertebrates, trilobites, mollusks, chordates, the ancestors of vertebrates, filled the planet with movement, predation, reproductive strategies, and ecological complexity. Life began weaving webs of interdependence with food chains, competition, and cooperation. At the same time, plants began colonizing the continents, followed by arthropods, and eventually by fish that gave rise to the first amphibians. From water to land, from land to air, life continued its creative march, adapting to each environment and experimenting with shapes and survival strategies. Earth thus became a truly living planet. Its surface was shaped not only by geological forces, but by billions of organisms breathing, photosynthesizing, feeding, and interacting. Every leaf, every drop of ocean, every layer of soil carried the signature of life. The blue planet was no longer just a rocky celestial body. It had become a global ecosystem in constant transformation, sensitive to its own creations. The biosphere became a geological force, and the atmosphere itself, rich in oxygen and nitrogen, was a direct byproduct of life's activity. We are heirs to this story. Every human cell contains organelles that originated from ancestral microorganisms. Every molecule in our bodies was once part of ancient oceans, old rocks, or extinct organisms. Earth is a dynamic stage where the chemistry of the universe found a rare combination of order, chaos, time, and matter to generate what we call life. And on this blue planet, lost among billions of galaxies, consciousness was beginning to take its first steps. Life, one of the most complex expressions of the known universe, had a modest and silent origin. From simple organic molecules formed in energy-rich, element-laden aquatic environments, Earth's first living organisms emerged around 3.8 billion years ago, during a time when the planet was still unstable, with active volcanoes, hot oceans, and a reducing atmosphere. These early life forms, similar to primitive bacteria, were prokaryotes, cells without a defined nucleus that reproduced by simple cell division and relied on basic chemical reactions to obtain energy. Though microscopic, they were the protagonists of a planetary-scale transformation, shaping not only the oceans but also the atmosphere, geochemical cycles, and eventually all life forms that would follow. These first organisms developed distinct survival strategies. Some absorbed environmental compounds and broke them down in exothermic reactions, a process known as chemosynthesis. Others learned to harness sunlight, giving rise to ionoxygenic photosynthesis, which did not release oxygen. But one special group of microorganisms, the cyanobacteria, began performing oxygenic photosynthesis, a revolutionary process that captured sunlight, converted water and carbon dioxide into glucose, and released molecular oxygen as a byproduct. This free oxygen, previously absent from the atmosphere, began to accumulate, radically altering the planet's chemistry and initiating the so-called Great Oxidation Event, which would cause mass extinctions among anaerobic organisms. As oxygen levels rose, new metabolic pathways became possible, including aerobic respiration, which is far more efficient than primitive fermentation processes. This allowed the emergence of organisms with higher energy demands and greater structural complexity. A crucial evolutionary step was the rise of eukaryotic cells, with internal compartmentalization, specialized organelles like mitochondria and chloroplasts, and a nucleus where DNA was more precisely protected and regulated. These cells didn't arise spontaneously, but through endosymbiosis, when one cell engulfed another, and instead of digesting it, formed a lasting symbiotic relationship. This ancestral union can still be seen today in every human cell. Our mitochondria are descendants of once independent bacteria. Evolution followed an upward trajectory in complexity. Eukaryotic cells began forming colonies where each cell performed a different role. Over time, this specialization led to the emergence of multicellular organisms, composed of billions of cooperative cells, coordinated by chemical signals and eventually nervous systems. The explosion of diversity that followed, known as the Cambrian explosion, around 540 million years ago, marked the appearance of most major animal lineages we know today: arthropods, mollusks, echinoderms, chordates. For the first time, eyes, skeletons, appendages, and complex behaviors emerged at a global scale in Earth's oceans. Evolution is driven by mechanisms such as genetic mutation, natural selection, genetic drift, and speciation. Small variations accumulated over millions of years in different environments resulted in the diversification of life forms adapted to distinct ecological niches. Some organisms specialized in swimming, others in crawling, flying, or climbing. The colonization of dry land, around 400 million years ago, was another extraordinary milestone. Plants came first, creating soil and stabilizing moisture. Then came arthropods and amphibians. Over time, reptiles, birds, and mammals conquered the continents, carrying with them the cellular complexity that had begun in the primordial ocean. All this diversity was made possible by genetic heredity, which enabled the storage, copying, and transmission of biological information across generations. DNA, a spiral-shaped molecule composed of nucleotides, carries the code of life in every cell. This code determines not only an organism's shape, but also its behavior, physiology, and environmental response. Over time, this same DNA has retained traces of Earth's entire history: mass extinctions, climate adaptations, migrations, and evolutionary leaps. In this sense, life is not just a chemical process, but a natural archive, where every species is a page written by billions of years of trial, error, and survival. The existence of life on Earth inevitably raises a larger question. Does life exist elsewhere in the universe? The basic ingredients, carbon, water, energy, organic molecules, are common in the cosmos. They've been detected in comets, moons of distant planets, interstellar clouds, and exoplanet atmospheres. Astrobiology, the science dedicated to understanding the conditions for life beyond Earth, continues to advance with every new discovery. Jupiter's moon Europa and Saturn's Enceladus have subsurface oceans protected by ice crusts. Mars once had rivers and lakes. Hundreds of planets orbiting other stars have already been identified in habitable zones. The universe is simply too vast for life to have emerged only once, and even if we have yet to detect other forms of life, our mere existence proves that life is a concrete possibility of matter. Life, then, is the temporary pinnacle of the universe's history, a moment where atoms learn to organize, replicate, and contemplate themselves. From the first sulfur-breathing bacteria to technological civilizations capable of sending interplanetary probes, the journey of life is a narrative of adaptation, resilience, and transformation. There is no divide between the physical universe and the biological one. We are the cosmos observing itself, thinking, and asking why we exist. As multicellular life diversified and the continents drifted across Earth's mantle, the planet entered a phase of colossal transformations marked by extinctions, rebirths, and the rise of some of the most impressive creatures ever to walk its surface. The Mesozoic era, which lasted for approximately 180 million years, from the Triassic to the Cretaceous, was dominated by the dinosaurs, land, sea, and flying reptiles that became the absolute rulers of every ecosystem on Earth. But simultaneously, in obscure and nocturnal corners, small furry animals with fast metabolisms and discrete habits began their own evolutionary journey, the bot mammals. This silent rivalry between two lineages would later lead to a dramatic reversal that would reshape the destiny of life on Earth. After the Permian-Triassic extinction, the largest annihilation event in Earth's history, around 250 million years ago, the planet was nearly empty of complex life. But this ecological void became fertile ground for new evolutionary forms. During the Cetan-Triassic, the first dinosaurs appeared in arid, unstable environments. Their bodies were lightweight, their postures upright, and their movements efficient. They quickly adapted to new conditions, diversifying into multiple groups: long-necked herbivores, bipedal predators, fierce carnivores, and semi-aquatic forms. Over time, during the Jurassic Time, these animals dominated the planet on a global scale, occupying everything from tropical forests to coastal zones. Some species reached 30 meters in length, while others developed feathers and complex social behaviors. Dinosaurs were not alone. In the skies, pterosaurs soared with membranous wings spanning up to 12 meters. In the seas, reptiles such as ichthyosaurs, plesiosaurs, and mosasaurs glided through the oceans with graceful movements, ruling aquatic environments. Meanwhile, terrestrial ecosystems flourished with gymnosperms, later followed by angiosperms, flowering and fruit-bearing plants that would radically change how solar energy was captured and redistributed. Biodiversity reached astonishing levels, and life grew more sophisticated through complex trophic cycles involving predation, cooperation, defense, and migration. Yet while dinosaurs commanded the stage, primitive mammals were evolving discreetly. Descendants of synapsid reptiles, they were small, nocturnal, and covered in fur that helped maintain body temperature. They fed on insects, lived in burrows, and cared for their young with greater dedication than most reptiles. Their brains were relatively larger compared to their bodies, and their nervous systems more developed. These seemingly modest traits would prepare mammals to endure catastrophic events that their giant neighbors could not survive. That catastrophe came 66 million years ago, at the end of the Cretaceous, when a 10-kilometer-wide asteroid struck the Earth in what is now the Yucatan Peninsula in Mexico. The energy released by the impact was equivalent to billions of nuclear bombs. Global fires, kilometer-high tsunamis, thermal shocks, and a dust cloud that blocked sunlight for months or even years plunged the planet into an impact winter. Photosynthesis collapsed, food chains disintegrated, and up on over 70% of all living species went extinct. Among them, all non-avian dinosaurs vanished. In this apocalyptic scenario, mammals survived. Their ability to regulate body temperature, their small size, subterranean lifestyle, and varied diet were decisive advantages. When the dust settled and sunlight returned to the skies, these small animals became the new colonizers of the ecological niches left by the ancient giants. The Cenozoic era began, and with it, the meteoric rise of mammals. They diversified into multiple orders: carnivores, herbivores, marsupials, primates, rodents, cetaceans. Some grew enormous like mammoths and woolly rhinoceroses. Others returned to the seas like whales. And one specific group, endowed with growing brains, opposable thumbs, and the capacity to live in societies, was preparing to revolutionize not just Earth, but the very consciousness of the cosmos. The history of life is neither linear nor predictable. It is shaped by extinctions and rebirths, by catastrophes and adaptations. Dinosaurs reigned for over 160 million years, far longer than all of human history, yet disappeared suddenly. Mammals, with their humble beginnings, took their place and changed the course of evolution. This succession reveals a deeper pattern of nature. Life persists, but never in the same form. It reshapes itself, adapts, reinvents. And every great extinction was, paradoxically, an opportunity for new forms to emerge and expand the limits of what is possible on planet Earth. With the decline of giant reptiles and the quiet expansion of mammals, the planet entered a new phase of biological experimentation. The diversity of forms, sizes, and life strategies increased across all environments: forests, savannas, oceans, mountains. But among all the groups that thrived during the Cenozoic, one in particular carried a rare and deeply transformative seed: intelligence. Over millions of years, small tree-dwelling primates gave rise to lineages increasingly adapted to environmental complexity. And at some point, between 7 and 2 million years ago, in unstable and challenging African savannas, the first hominids emerged, direct ancestors of modern humans. These hominids stood out not only for their upright posture and skillful hands, but also for their increasingly large brains. The encephalization quotient, the ratio between brain size and body size, grew with each new species. The advantages were not immediate. Larger brains consume more energy, require more parental care, and extend childhood. But they also allowed for more sophisticated processing of sensory, social, and environmental information. The first members of the genus Homo, such as Homo habilis, began to manipulate tools, breaking stones to cut meat, dig, scrape. These simple actions represented a leap. The mind began to extend beyond the body, using the world as an extension of will. Over time, species like Homo erectus and later Homo heidelbergensis mastered fire, developed rudimentary languages, migrated across continents, built shelters, and formed complex social bonds. Survival was no longer enough. It became essential to cooperate, remember, plan, teach. Social cognition, the ability to understand others' intentions and emotions, became central to survival. With it came the roots of empathy, morality, and culture. The human brain, especially the prefrontal cortex, continued to grow, becoming a center for internal simulations where future events could be imagined and decisions evaluated before being acted upon. Around 300,000 years ago, Homo sapiens emerged. Gifted with articulate language, self-awareness, the ability to symbolize and abstract imagination, this new kind of animal did not just adapt to the world, it began to shape it. Cave paintings, ritual burials, myths, dances, refined tools, and eventually agriculture, architecture, and writing. All of these arose from the spark we call consciousness. The universe, after 13 billion years of existence, had finally produced something capable of looking at the stars and asking where it came from. This consciousness did not appear as an isolated leap, but as the result of a cumulative process in which biology, environment, and culture interacted in constant feedback loops. A larger brain favored better social strategies. More complex societies pushed for higher cognition. As language developed, it allowed knowledge to be passed across generations, accelerating cultural evolution. Through it, stories, ideas, and symbols began to shape behavior, creating traditions, religions, belief systems, and science. For the first time, evolution no longer depended solely on DNA but also on collective memory. Humans spread across all continents, facing extreme climates, dangerous megafauna, and challenging environments. But the true revolution came when they began to transform nature, domesticating animals, cultivating land, building cities. This transformation brought new pressures: disease, inequality, conflict, but also art, philosophy, mathematics, and astronomy. Human intelligence turned not only toward immediate survival, but toward contemplating the infinite: time, death, space, gods, and the universe itself. We are, as far as we know, the only form of life capable of understanding its own stellar origin, biological evolution, and ecological fragility. Every atom in our bodies once belonged to dead stars. Every thought, no matter how complex, is a pattern of electrical synapses emerging from organized matter. But as we contemplate this trajectory, from the Big Bang to neurons, we realize that human intelligence is not an isolated accident, but a natural chapter in the long cosmic story. A story in which matter learned to think. With the emergence of human consciousness and the progressive mastery over the environment, the history of life on Earth entered a new era, no longer defined solely by geological events or biological cycles, but by the conscious action of a species capable of shaping the world around it. After hundreds of thousands of years living as hunter-gatherers in small nomadic tribes spread across savannas, forests, and tundras, humans took an unprecedented step in evolutionary history: the domestication of nature. This transformative moment began around 10,000 years ago, with the advent of agriculture, which redefined the foundations of survival, reorganized social relationships, and enabled the rise of the first civilizations. The agricultural revolution was not sudden, but the result of observations accumulated over generations. In regions like the Fertile Crescent in the Middle East and in fertile river valleys such as those of the Nile, the Indus, and the Yangtze, humans began cultivating grains, domesticating animals, and establishing permanent settlements. Control over food production freed part of the population from the task of finding sustenance, allowing the emergence of social specializations: farmers, blacksmiths, priests, leaders, soldiers. Cities arose as centers of storage, exchange, and power. Writing was invented to record harvests and taxes, and soon became a tool to transmit knowledge, mythology, and laws. Thus were born the first urban, bureaucratic, and symbolic structures of civilization. With cities came states. Empires grew around rivers and trade routes, developing legal systems, currencies, calendars, armies, and complex social hierarchies. Civilizations like the Sumerians, Egyptians, Chinese, Maya, Greeks, and Romans created legacies that endure to this day. They developed mathematics, geometry, astronomy, and philosophy, and took the first steps in understanding the laws of nature. They looked at the skies not only with fear, but with method. They built observatories, recorded eclipses, mapped constellations. For the first time in Earth's history, nature began to be understood from within, rationally and empirically. The invention of the printing press in the 15th century accelerated the dissemination of knowledge, breaking the monopoly of religious and political elites. The scientific revolution, centuries later, solidified the systematic investigation of the physical world. Galileo observed Jupiter's moons, Newton described gravity, Darwin understood evolution. Humanity began to see itself not as the fixed center of the universe, but as part of a larger cosmic system in constant flux. Ideas ceased to be merely inherited traditions and became testable, revisable, verifiable theories. Science transformed how we perceive time, matter, energy, and ourselves. The Industrial Revolution in the 18th century took this capacity to a new scale. The use of fossil fuels, machinery, electricity, and global transport networks connected billions of people and reshaped entire landscapes. For the first time, humanity began to systematically alter the climate, oceans, forests, and the carbon and nitrogen cycles. Transformative power grew exponentially, and with it came new challenges: pollution, inequality, technological wars, energy crises. But incredible advances also emerged: vaccines, computing, mass education, artificial intelligence. The information age, launched in the 20th century, pushed human consciousness to new frontiers. Satellites orbit the planet in real time. The internet links billions of minds. We've sequenced the human genome, sent probes to other planets, detected gravitational waves and photographed black holes. We live in an era where the species that once walked savannas now had simulates universes inside computers. With algorithms, telescopes, and particle accelerators, we reconstruct the cosmic past and project possible futures. Civilization has become a geological force, and many scientists now argue that we live in a new epoch called the Anthropocene, the age in which humans became the dominant agent on the planet. But this power came with no guarantees. Every civilization carries within it the risk of self-destruction by war, ecological collapse, or social imbalance. The technology that liberates us also challenges us. That's why the development of civilizations marks a turning point in the history of the universe. It is here that consciousness must learn to self-regulate, protect itself, and protect the planet that sustains it. Intelligence, to persist, must be wise. It must remember that although we are made of stars, we are still fragile. The universe is vast, but the home of known life, so far, is only one. Every civilizational advance is, at its core, a continuation of the long evolutionary chain that began billions of years ago. Fire, the wheel, writing, the telescope, the satellite, all are extensions of the human mind, which is itself an expression of cosmic matter. From stardust to data servers, from stone tools to quantum engineering, the story of civilization is the story of how the universe became capable of thinking about itself and acting consciously upon its own trajectory. When the first humans looked up at the night sky, the firmament seemed like an unreachable mystery, a dark ceiling studded with points of light, full of myths, gods, and omens. For millennia, the stars were read as oracles, the planets as wandering deities, and eclipses as divine warnings. But behind the legends lay a fundamental desire to understand. Where did we come from? What lies beyond? Where are we going? This ancestral impulse, which moved Mesopotamian skywatchers, Islamic astronomers, and Renaissance mathematicians, found its boldest realization only in the 20th century, when humanity, for the first time, left its home planet. Space exploration represents a new chapter in the history of cosmic intelligence, the moment when a species evolved on a microscopic point in the universe decided to recross the boundary of the atmosphere. The first step came in 1957 with the launch of the Soviet satellite Sputnik, a metal sphere that transmitted a simple radio signal, yet echoed like thunder in global consciousness. 2 years later, the probe Luna 2 impacted the moon's surface, and in 1961, Yuri Gagarin became the first human to orbit the Earth. Space, long unreachable, became a territory of inquiry. The crowning achievement of this pioneering era was, without a doubt, the Apollo 11 mission, when in July 1969, Neil Armstrong and Buzz Aldrin set foot on the lunar surface. The words, "one small step for man, one giant leap for mankind," resonated not just as a technological triumph, but as an ontological statement. Life from Earth had touched another world. For the first time, we could look directly at our planet from space, a blue, fragile globe floating in the void. That perspective profoundly reshaped human views on ecology, politics, and planetary belonging. The space race between the United States and the Soviet Union was only the beginning. In the decades that followed, space shifted from a field of geopolitical demonstration to a laboratory for international scientific cooperation. Missions like Sun Voyager 1 and 2 Kia, launched in 1977, crossed the edges of the solar system, sending back data on Jupiter, Saturn, Uranus, and Neptune, and carrying the famous Golden Record, with messages and sounds from Earth destined for potential extraterrestrial civilizations. The International Space Station, built starting in the 1990s, became a symbol of international unity and a platform for research in biology, physics, and medicine in microgravity. Beyond crewed flights, robotic exploration has revolutionized our understanding of the cosmos. Probes like Curiosity, Perseverance, Cassini, Juno, New Horizons, and many others have allowed us to study the geology of Mars, Saturn's rings, the hidden oceans of Enceladus and Europa, and even capture detailed images of Pluto, once just a blurry speck. With each mission, we discover a universe more dynamic, complex, and astonishing than we imagined. Space is not an inert void. It is a stage of solar storms, underground oceans, ice volcanoes, and exotic atmospheres. But space exploration is not just about observation. It is prospecting the future. The search for life on other planets, the possibility of terraforming, asteroid mining, and colonization of moons or Mars are no longer mere science fiction. Private companies like SpaceX, Blue Origin, and Rocket Lab, along with agencies like NASA, ESA, Roscosmos, and CNSA, are working to make permanent human presence beyond Earth a reality. With reusable rockets, modular habitats, and artificial intelligence, the vision of a key multi-planetary civilization is under construction, though still wrapped in deep technical and ethical challenges. Space exploration also helps us understand the origin and fate of the universe itself. Space telescopes like Hubble, and more recently James Webb, allow us to observe galaxies formed shortly after the Big Bang, study the atmospheres of exoplanets, and analyze light so ancient it nearly touched the beginning of time. Looking into the cosmos is looking into the past. Each photon captured by these instruments is a messenger that traveled billions of light years to tell its story. And by deciphering it, we draw closer to the truth of how it all began and how it all might end. But perhaps the greatest impact of space exploration is neither technical nor scientific. Perhaps it is existential. The very fact that we have crossed our biosphere is a powerful affirmation. We are part of the universe, and we have the right and the duty to know it. Each launch, each probe, each photograph of the cosmos is an extension of the curiosity that began with early humans sketching constellations in caves. The difference is that now we have rockets, antennas, and particle accelerators. But the question remains the same. Where are we? And more importantly, are we alone? Exploring space reminds us that the universe is not just our backdrop, it is our origin and our destiny. And as we reach for the stars, perhaps we are simply coming home. Since the moment the universe was born, about 13.8 billion years ago, it has been in constant expansion. Space, time, matter, and energy stretch like a vast cosmic sheet where galaxies move away from one another, not because they are traveling through fixed space, but because the very fabric of space is growing. This expansion was first detected by Edwin Hubble in the early 20th century through his observation of redshift in the light from distant galaxies. From this discovery, scientists realized the universe is not static, it is in motion. And like everything in motion, it follows a trajectory leading to the inevitable question: what will be the final fate of the universe? At first, it was believed that gravity might eventually slow down the expansion, maybe even reverse it, leading to a cosmic collapse known as the Big Crunch, a catastrophic return to the singularity state. But more recent observations, especially those made in the 1990s using Type Ia supernovae, the Hubble Space Telescope, and other missions, revealed something astonishing. The expansion of the universe is not slowing down, it is accelerating. This finding defied expectations that gravity should pull everything back. Something unknown, a form of energy that does not interact with visible matter and fills the vacuum of space, is pushing the universe outward. This phenomenon was named dark energy. Dark energy makes up about 70% of the universe's total content. Unlike matter, it does not clump together, nor does it form galaxies, stars, or planets. Its only known effect is to accelerate cosmic expansion. Yet its true nature remains one of the greatest mysteries of modern science. Is it a cosmological constant, as Einstein once proposed? Is it a type of quantum field? Or is it merely a reflection of a deep gap in our understanding of gravity? While physicists try to solve this enigma, one thing is certain: it is dictating the fate of the universe. If dark energy continues to behave the same way indefinitely, the universe will expand eternally in a scenario known as the Big Freeze. In this future, galaxies will drift so far apart that they will vanish from view, separated by vast oceans of empty space. Stars will burn out one by one, exhausting their fuel and collapsing into white dwarfs, neutron stars, or black holes. With no new star formation, the universe will become a dark, cold, and silent place, an eternal night where matter, too sparse, will be unable to generate light or heat. In trillions of years, even black holes will evaporate via Hawking radiation, and the universe will reach thermal death, with maximum entropy and no energy gradients to support meaningful physical processes. But other possibilities exist. If dark energy increases in intensity over time, the universe could face an even more dramatic fate, the Big Rip. In this scenario, expansion doesn't just continue, it accelerates to a point where galaxies, solar systems, planets, molecules, and even atoms are torn apart by the stretching of space itself. On a timescale that depends on the exact properties of dark energy, everything would disintegrate. Reality would lose all cohesion, and the very fabric of space-time would be destroyed. There is also a third hypothesis, the Putty Big Bounce. In this theory, the universe would expand up to a certain point, but for reasons not yet understood, dark energy would change its behavior, allowing gravity to regain control. The universe would then begin to contract slowly, heating up as galaxies collapsed into one another, until reaching a new singularity, and then perhaps initiating a new Big Bang. This cyclical model suggests the cosmos may go through infinite phases of birth, growth, collapse, and rebirth, in an eternal dance of creation and destruction. Which of these outcomes is correct remains unknown, but regardless of the final scenario, one thing is clear. The universe is not a static stage. It is a mighty, dynamic process, a story in motion. Every star that shines, every planet that orbits, every atom that vibrates is part of this flow. The arrow of time points toward expansion, transformation, and perhaps dissolution. Yet this same arrow allowed the universe to evolve from a particle soup into galaxies, stars, life, and finally into intelligence that now contemplates its own origin and end. To ponder the fate of the universe is, paradoxically, to reflect on our own mortality and meaning. We are creatures of an expanding cosmos, made of stardust, conscious for a brief instant amid trillions of years. But in that instant, we write, discover, love, create, and question. Whether the universe ends in cold, in fire, or in renewal, this fleeting awareness is proof that matter can dream, and time, for a moment, can be understood. The history of the universe is a colossal narrative of transformation, and to understand it fully, we can organize it as a cosmic timeline, a sequential map of the most important events from the initial moment to the still unknown horizons of the future. This timeline is not made of ordinary days or years, but of epochs, eras, and transitions, where matter, energy, and space evolved in unimaginable ways. With each phase, the cosmos became more structured, more complex, more self-aware. And although everything began from a dimensionless point, today the universe spans billions of light-years in diameter and carries within itself the memory of every instant that shaped it. Is seconds, the Big Bang. The universe is born as an infinitely hot and dense singularity. Space and time come into existence. The cosmos begins to expand. In this first instant, all the forces of nature were unified. There was no matter, only pure energy. 1/10,000th of a trillionth of a second. Cosmic inflation. The universe undergoes exponential expansion. Microscopic quantum fluctuations are stretched to macroscopic scales, creating the seeds of galaxies. Symmetry among the forces breaks. Gravity separates from the other forces. 1/1,000,000th of a second, formation of fundamental particles. Quarks, electrons, and neutrinos emerge from energy. Quarks group to form protons and neutrons. 3 minutes, primordial nucleosynthesis. The universe cools enough to allow protons and neutrons to combine, forming the first nuclei of hydrogen, helium, and traces of lithium. 380,000 years, the recombination era begins. Electrons bind to nuclei, forming neutral atoms. Light is finally able to travel freely through space. The cosmic microwave background is released, a photograph of the baby universe. For 100 million years, end of the Dark Ages. The first population 3 stars are born. The era of rionization begins. Radiation ionizes surrounding hydrogen, illuminating the universe. 1 billion years. Formation of the first galaxies. Gravity organizes matter into rotating structures of gas, dust, and stars. Galaxies collide, merge, and evolve. Supermassive black holes emerge at the centers of the largest galaxies. 9 billion years. Formation of the solar system. A heavy element-rich interstellar cloud collapses, forming the Sun, and around it planets, moons, asteroids, and comets. Earth emerges as a rocky planet in the habitable zone. 9.2 billion years. Formation of the Moon. A massive impact between Earth and a Mars-sized body creates our natural satellite, which stabilizes Earth's axial tilt and influences tides. 10 billion years. Origin of life on Earth. Simple organic molecules organize into self-replicating structures. The first unicellular prokaryotic organisms appear. 11 billion years. Oxygenic photosynthesis begins. Cyanobacteria start releasing oxygen into the atmosphere, dramatically altering the planet's chemistry. 12 billion years. Cambrian explosion. Complex multicellular life forms arise. Eyes, skeletons, predators, and sophisticated ecological relationships appear. 13 billion years. Dinosaur extinction. An asteroid hits Earth. Large reptiles go extinct. Mammals survive and begin their rise. 13.7 billion years. Emergence of Homo sapiens. Consciousness arises. Humans develop language, culture, art, technology, and spirituality. 13.799 billion years. The space age begins. Humans cross Earth's atmosphere. Probes are sent to other planets. Distant galaxies are observed. Humanity begins expanding beyond its homeworld. 13.8 billion years. The present. The universe continues accelerating its expansion. Dark energy dominates. Human civilizations study the cosmos and project futures. Distant future. Cosmic destiny. Depending on the behavior of dark energy, the universe may end in a big freeze, big rip, or big bounce. Stars fade, black holes evaporate, and space becomes a thermal void. Or perhaps the cycle begins again. This timeline is more than chronology. It is the story of energy becoming matter, matter becoming complexity, and complexity becoming consciousness. It shows that there was not a single moment of creation, but a continuous process where everything evolves, from atom to galaxy, from microbe to human, from silence to question. Time is the framework of all that exists. And we, brief passengers of this immense current, are also part of the story. Not merely observers, but living chapters of the journey of the universe. When we contemplate the vastness of cosmic history, from the first photons to human consciousness, from primordial galaxies to artificial intelligence, we realize that the universe is not merely a collection of stars and planets, but a process of self-organization in search of complexity, structure, and meaning. From primordial chaos emerge the laws of physics, from elementary particles atoms, from atoms molecules, and from molecules living cells. Over 13.8 billion years, the cosmos has become something that thinks, feels, and questions its own existence. And in this process we, fragile beings made of carbon and water, have emerged as the eyes and the voice of the universe. Earth, a small blue planet in a spiral arm of the Milky Way, harbors the only known life in the cosmos. This does not mean we are alone. It means that for now we are the only conscious expression of the universe capable of telling its story. This condition places us in a paradoxical position, insignificant in the scale of space and time, yet absolutely essential as observers and narrators of this universal history. Without consciousness, the universe would exist in silence. With it, it gains language, music, art, love, science, memory, and future. The legacy of the universe is not only in its physical structure, in galaxies, black holes, and quantum fields. It is also in every human gesture of contemplation and discovery, in every child who looks up with curiosity, in every scientist mapping stars, in every artist translating infinity into color and sound. The universe has given us everything: the air, the light, the atoms in our bodies, the gravity that holds us up, the cycles of tides and seasons, the elements that make up DNA, the rhythms that sustain life. We are both the result and reflection of the cosmos. We are made of it, and we will return to it. Our role, therefore, is twofold: to care and to understand. To care for the only planet we know to be habitable. To understand the universe not only as a scientific pursuit, but as a path toward wisdom. This awareness demands responsibility, ethics, empathy, humility. Earth is fragile, civilizations are unstable, life is rare. But as long as there is a human who looks to the stars and wishes to understand, the universe will be, in a way, awakening in itself, a spark of eternity. When we gaze into the night sky, we see light that has traveled for billions of years to reach our eyes. Some of those stars no longer exist, but their light still touches us. We are like that too, passengers through time, whose actions, ideas, and memories may echo far beyond our lifetimes. Each human life is a point of light in the great map of cosmic consciousness. And whether this universe ends in cold, in fire, or in rebirth matters little. What matters is that, for a brief moment, the universe knew it existed and called itself humanity. The history of the universe does not end. It continues in every glance, in every discovery, in every step we take toward the unknown. From nothing to infinity, we are part of this whole, and perhaps, just perhaps, its deepest purpose.